Good morning.
It is that time. Everybody have their breakfast and their coffee and you ready to go? All right. Put a bookmark here. Shut that up. Oh, here's the iPad. Gotta use this. All right. We are world champions today. It's always nice when you're a world champion. I hope none of you lost any fingers or toes in the celebration. Lots of fireworks going off downtown LA, it looked like. I didn't hear any in Camarillo. Excuse me.
There were quite a few in Oxnard, that's for sure.
Yeah.
Yeah, there was a lot in my neighborhood, so that was fun.
When I was walking the dog last night, the game was on. Of course, I wasn't watching it, but we'd hear all kinds of shouts coming out of apartments and stuff, cheering what was happening on the game. Lots of people were excited. Lots of people were watching. Maybe next year the Twins will win. It's been a while since they won. I think they last won in '89, so they're in line, right? The last Dodger World Series win was '88. Was that what I was hearing last night? So it's time for the Twins to win. Maybe they won before then. All right, enough baseball. Is there anything anybody wants to talk about, bring up regarding what we're doing, etc., etc.?
Would we be able to do like an example or two with like derivatives dealing with inverses?
Yeah, actually, I will talk about that today. In fact,
Oh, okay.
um, yeah, I think I'm just gonna do a couple more challenging examples. But my plan is to do a couple more challenging examples with the chain rule, and then I will talk about what's called the inverse function theorem, and how now that we know the chain rule, we can apply that to find formulas of inverse functions, which is cool. And then I'll show you a couple examples for how to do that. So I'm a little distracted here as I prep my notebook for today. It's the 28th. Okay. Two more steps and I'm ready. Is there anything else anybody else wants to talk about today? Not hearing anything. So let me share my iPad and we'll get going. So Haven, you said you're trying to watch past lecture videos, but they said they were unavailable private. Okay. Let's deal with that. Somebody else told me the same thing. So I'm sharing my browser. Let's get into Canvas. You can do it. All right. Haven, can you tell me which one you were having a problem with, if there's a specific one? All of them. So all the videos you were having problems with, huh? All right, it seems like I can see it, but that shouldn't be a surprise, right, if I own them. So let me just spend one moment here and see if it's a quick fix. I'm going to look for all the private ones. It looks like there's no private videos here. Someone listed in some draft. So let me make a note to take a look at this after class. So we're talking 28 October. Okay, so we've got a request for me to figure out what's happening with these videos and a request to talk about derivatives of inverse functions. So I'll make sure both those things happen today. All right. I'm getting a message that my internet is unstable, so I will throw in a chat if you see my video updating slowly or whatever, and I'll try to adjust. So what I'm going to do today, as I said, in addition to these two things, I'm going to do a couple more examples of the chain rule. And they're just more difficult examples, and I want you to see a couple more difficult, challenging examples worked, because I want you to be able to do it. Then I'm going to talk about the inverse function theorem. Okay, so that's going to speak to Robert's question. And then I'm going to oh, come on. Weird. Then I'm going to talk about implicit differentiation. So this is an important application of the chain rule. And it lets us calculate derivatives of functions that maybe we don't even have explicit formulas for. It's kind of a fascinating thing. Important technique, implicit differentiation. And then hopefully I'll have time to start talking about this topic of that's called related rates. Okay, these are word problems. And this will start our work in chapter 4. And then it also starts our work on the learning target quizzes in area A for applications of the derivative. There's one more topic in area D that we haven't talked about. I think it's L'Hopital's rule. I might make a screencast about that you can watch next week, next Wednesday. Right, so this is the plan for today. Okay, we're going to finish up chapter 3, maybe start chapter 4. And, we're really going to be finishing up the top topics of our the topics related to differentiation. Yeah, so I'm seeing in chat that my audio is cutting in and out. I'm also talking kind of funny this morning. I'm kind of having a lot of pauses in my voice. And it's really laggy, you say. So give me a second to think. Re-sign in. All right. Why don't I'm going to log out and log back in, and I'm going to make Lupe a co-host. And when I leave, he'll become a host, but then I'll come back in right away. Okay, so Hangout, we'll see if anything improves. Thanks, Selena. Yeah, I'm recording now. So let me do a couple more involved examples of the chain rule. So let's take the derivative of 2 to the x sine squared x. So one of the things we were practicing on Monday is when you see a problem, you need to identify a first step, or what's the first thing you need to do. You overcome that activation barrier. So I'm looking at this thing and I'm saying, I need to take the derivative. What do I need to do? Well, the first thing I see is I've got to do the product rule. So that's the first thing I need to do. So the product rule says it's the derivative of a product is the derivative of the first times the second plus the first times the derivative times the derivative of the second. Okay. Now I look at what I have here and ask the question, what do I need to do? Well, I need to do what the derivative tells me to do. So here I need to calculate the derivative of 2 to the x. I've got a formula for that, so that's cool. Nothing needs to be done there. Nothing needs to be done there. So this here, how do I calculate this derivative? Well, that's a chain rule problem, right? This is like the sine of x squared. So I've got to be prepared to do the chain rule there. So let's do it. So the derivative of 2 to the x is log 2 times 2 to the x. That's the derivative formula we have. Nothing with that sine squared, nothing with this 2 to the x. Now the derivative of sine squared, okay, we're going to use the power rule. So we get 2 times sine to the first power. And then since we've got a trig function inside the power, we have to use the chain rule and multiply by the derivative of sine. So there we go. That's how we calculate the derivative. Now, if I want to simplify it all, and it's probably a good idea in this case to simplify, what I can do is I can say, well, are there any common factors that I can factor out? Well, I've got a sine in the second term, and there's two sines in the first term. And there's a 2 to the x in the second term and a 2 to the x in the first term. So I can factor those out. So I can say 2 to the x sine x times the quantity, and then what am I left with? Log 2 sine x plus 2 cosine x. Right, and that's a nice way to leave my answer. Any questions about that? Okay, let's do another one. Let's calculate the derivative of the square root of x plus the square root of x plus the square root of x. All right, this is kind of gnarly. Lots of square roots here. And you can see the nesting, right? So you can see there's compositions happening here. I've got a square root function here inside this other square root function, which sits inside this other square root function. So when I look at that and I say, what's the first thing I need to do? the first thought that comes to my mind is chain rule. I'm definitely going to need to use a chain rule, and maybe even more than once. So let's do this. What I'm going to do is I'm going to change these square roots to exponents because we'll be using the power rule. So there we go. So this x plus square root of x, that's right here. And then that's all to the 1/2 power. And then this is here, right? And so that half power goes along with this square root. And then this half power goes along with this square root. So that looks good. So let's do it. Taking the derivative of this whole thing, this is on the inside of this half power. So I get I get using the power rule, then I'm going to rewrite what's inside. And then to the minus 1/2. And now I use the chain rule, so I've got to put the derivative of all this here. Right. So over here, the derivative of this is this. So the derivative of the sum is the sum of the derivatives. So the derivative of x is 1. And the derivative of this over here, I need to use the chain rule again. So rewriting. So that all stays the same. That's just kind of a pain to write. And now as I evaluate the derivative, I get 1 plus, and we're going to take the derivative of this. So again, first start with the power rule. Okay, power rule is done. Now the chain rule says I need to multiply by the derivative of the thing that's on the inside. Okay. So now in the next step, aside from having a lot of stuff to recopy, I'm just going to recopy it. I'm going to take this derivative here. And here I'm going to use the sum rule. So the derivative of this sum is the sum of these two derivatives. And so I get the derivative of x is going to be 1 and the derivative of x to the 1/2. I'm just going to use the power rule. So all the complicated stuff is done. Right, and that's the derivative. That looks gross. But as long as you keep track of all the details at every step, you'll be fine. I could take this one more step further, and I could change these things back to radicals. And so the first term would look like this. And the second term would look like this. And my numerator up here would look like 1 plus 1 over 2 the square root of x. All right, and so that would be a nice way to leave the derivative. But if I was asking you to do this on an assignment and just asking for the derivative, that would be a reasonable place to leave it. All right, let's do one more. Let's calculate the derivative with respect to t of e to the t sine square root t. All right, so you can see the composition here. I've got an exponential function, and inside that exponential function, I've got that function. So I look at this and I see, oh, this is a chain rule problem. That's going to be my first step. So the derivative of an exponential is that exponential again. And then since the thing inside my exponential is complicated, the chain rule says I need to multiply by its derivative. So what do I do next? Well, I've got to calculate this derivative. And I've got a function here in t, and I've got a function here in t. They're multiplied together, so I've got to use the product rule. That's the next thing I have to do. So recopying. I get the derivative of t, which is 1, times the second function, plus t times the derivative of the second function. And I'm just going to write it this way because the second function itself is complicated. And so just by writing this down, it gives me a second to pause in my calculations. I don't need to do everything at once. So looking at this, I see that I've got a trig function, sine, and in it, I've got a complicated function of t, the square root of t. So this also tells me I'm going to use the chain rule. So e to the t sine square root of t times sine of square root of t plus t times, okay, so here we go. The derivative of a sine is cosine. And then now I multiply that by the derivative of the square root of t, by the chain rule. And calculating the derivative of the square root of t, that just uses the power rule. So that will be my last computation, it looks like. That's kind of nice. So recopying all this work I've done. And the square root of t, its derivative is 1/2 t to the minus 1/2. And there you go. You could stop there. That would be a reasonable thing to do. But you could see that this term and this term, you could consolidate those, right? That constant you could pull out to the front. But the law of exponents says that t and t to the minus 1/2, they can be combined. And so you can do one more very reasonable simplification and say this is sine root t plus 1/2 square root of t cosine square root of t. And that would be a nice expression to leave and end with. Okay. Doing this one step at a time is really the key. Don't let yourself get intimidated by the problem. Allow yourself just to take it one step at a time. There's no way I can look at this and anticipate what I'm going to end up with. I can't look into the future that way. And I've been doing this kind of stuff for 20 years. I just do this one step at a time and until I get to the end. And so you should too. And that key of asking, what's the next thing I need to do? If you can get comfortable with that, sticking your neck out and taking the next step, that'll take you 1,000 miles in mathematics. In the end, if you want to check to see if that this work is right, plot this. Plot this function at on the same axis with this function, and look to see if you see the signs that this represents the rates of change of this, right? The slopes of the tangent lines. Okay, so that's where I'll leave the chain rule. And I just encourage you to practice with the chain rule. So let's talk about this inverse function theorem. Robert asked that. I mean, he's been very patient. He'd asked this question before. How do you take the derivative of inverse functions? So we know all kinds of functions are invertible. So a function's invertible if its graph passes the horizontal line test. And then if you have a graph of a function and you know it passes the horizontal line test, how do you figure out what its inverse is? Well, you flip it around the line y equals x. Right, you reflect about this line y equals x. And I think in this case, it looks like the graph kind of looks like this, and my iPad is being glitchy. So what I want to point out to you is we want to ask the question, and Robert's asking this question. If I've got a function that's invertible, is its derivative going to be invertible? And if it's, or is its inverse going to be differentiable? And if its inverse is differentiable, then what's the derivative of the inverse? And those are great questions to ask. And so what I'll point out to you is that if a graph passes the horizontal line test and the graph is differentiable, that means it's right, it's invertible and it's nice and smooth. And because the inverse function is just a reflection of the original function, that means the inverse function is going to be nice and smooth. And so we would fully expect that if a function's invertible, then its inverse is going to be invertible too. We'd fully expect that from the geometry. And in fact, you can, I'll just leave that there. So the geometric picture suggests that if a function is differentiable, its inverse will be differentiable too, because of qualities of the graph. And what are some inverses that we know about? Let's see, what's an inverse that we know about? Well, the exponential function, it has an inverse, it's the natural log. The square root function, well, let's say the squaring function has an inverse, it's the square root function. For that matter, x to the n for an accounting number has an inverse, it's x to the 1 over n. And so we know lots of functions that have inverses. In fact, we can talk about trig functions and create situations where they're invertible. I won't talk about those today. But this this thing that's called the inverse function theorem will give us a formula for inverses and for their derivatives anyway. Specifically, it's going to give us a formula for the derivative of the natural log, which isn't something that we have yet. We don't have a formula for the derivative of the natural log. So the inverse function theorem says that if f of x is invertible and differentiable, then its inverse, f inverse of x, is also differentiable. Moreover, the derivative of the inverse is 1 over the derivative of f. And the formulas don't get nicer than this. The derivative of an inverse function is the multiplicative inverse of the derivative. That's pretty sweet. That's pretty sweet. So let me show you why this is true, and then we'll use it to derive a derivative formula for the natural logarithm. So here's the proof, actually. Since f of x is invertible, there's a function f inverse of x where f composed with f inverse of x is just x. That's the definition of what it means for a function to be invertible. So I just want to note that if we call f inverse of x y, then f of y equal f of y equals x. So that's the relationship between the input and the output of f and f inverse. So let's take a look at this equation here. And let's differentiate both sides. And we're going to differentiate it with respect to x, right? This input variable. So on the right-hand side, that's like the easiest derivative ever. That's just the number 1. On the left-hand side, we have to use the chain rule. So the chain rule tells us the derivative is f prime evaluated at f inverse of x times the derivative of f inverse of x. So this is what we want to find a formula for. What's the derivative of the inverse of a function? So I'm just going to divide both sides by this. Right, and that's what we wanted to prove. So that's the whole proof. Okay, that's the inverse function theorem. Why is my iPad doing this today? So let me just show you some notation. F prime of f inverse of x. That's the same thing as saying df dx or df dy evaluate at y equals f inverse of x. Okay, so I'm bringing back this notation I introduced a while ago and haven't used too much. But now using the inverse function theorem, it's kind of helpful to give us a reminder that first we're taking the derivative and then we're plugging a value into the derivative. And that's important here because x is not the input of f and f inverse at the same time. They've got different domains, right? Their domains and ranges are opposite from one another. So let's use the inverse function theorem. To find the derivative of the square root function. Okay, and so we're going to use the idea that the square root of x, the square root function and the squaring functions are inverse. So let's let f of x be x squared. So the inverse of f is the square root of x. So the inverse function theorem tells us that the derivative of the inverse function is 1 over the derivative of the function evaluated at the inverse of the function. I'll bring this over to the next page. For us, f prime of x is 2x. Okay, so the derivative of the square root of x, according to the inverse function theorem, is 1 over 2 times f inverse of x. right? The derivative of f here is twice the input. So my input here is f inverse of x. And what's f inverse of x? Well, it's square root. So this is how we would calculate the derivative of the inverse of the squaring function using the inverse function theorem. Now, you're sitting here saying, Miller, we don't care. We can calculate the derivative of this thing directly using the power rule. And I say, yes, you're right. But here, what I wanted to show you is that the inverse function theorem is consistent with everything that we've done so far. It gives us the same derivatives as it would with our power functions. And I also want to remind you that when we introduced the power function the first time, I could only prove it for integer exponents. I couldn't prove it for anything else. The square root function is x to the 1/2. That exponent is not an integer. So technically, we don't know. You're just taking on faith that the derivative of the square root function is this, that the power rule works. Today, I proved to you that it works. In fact, with the inverse function theorem, you can prove the power rule works. The power rule for derivatives works for all rational exponents. So in a way, this is important. In a way, it's not that important. But it's a nice example to show that the power rule and inverse function theorem are consistent with one another. Now let's do something that we need to do. Let's use the inverse function theorem to calculate the derivative of the natural log function. All right, I just got a message from my computer that my internet is unstable, so please let me know if you see glitches, and I will continue with this example. So for this example, let's let f of x equal e to the x. So f prime of x equals e to the x as well. And the inverse of e to the x is log x. And we want to calculate the derivative of log x. So by the inverse function theorem, the derivative of the inverse, so in our case log, the natural log, is 1 over the derivative of f at the inverse. So our derivative function is e to the x. So this is 1 over e to the f inverse of x. And our f inverse is log. So that's 1 over e to the natural log of x. And you look at that and you say, hey, there's an identity. I can simplify that. Indeed, we can. This is 1 over x. All right. So that's cool. So I'm going to turn the page and write down a new derivative identity that we have. And let's write this down as a theorem. The derivative of the natural log of x is 1 over x. And I need to check this, but the derivative of the log base b of x is 1 over the natural log of b times x. All right, so those are our new derivative formulas for the natural logarithm and a general logarithm. So this increases the collection of functions you know how to differentiate. Another question for you to think about is consider f of x that's differentiable it's differentiable and passes through the point x naught, y naught. How does the tangent line to the graph of f of x at x naught, y naught compare to the tangent line to the graph of the inverse function at y naught, x naught? All right, that's a nice thing to think about to help become more comfortable with the ideas of functions, inverse functions, and their derivatives. There's a nice little relationship between those tangent lines. All right, we're at 8:45. I'm ready to switch to the topic of implicit differentiation. So let me introduce it for a moment, and then we'll take a break and do some examples. But let me ask, Robert, does this answer your question about derivatives of inverse functions? Do you have any other ones you want to ask?
No, you covered all of it. Thank you.
Okay, you're welcome. Okay, so the next thing we're going to talk about is implicit differentiation. And so far in the course, we've talked about situations where we have an independent variable x and a dependent variable y, and they're related through a function that can be written in this way. And we say that y is an explicit function of x. And it's explicit because it's expressed through this function f, and all the x's are on one side of the equation. Right? We don't have any y's on the right hand side of the equation. We don't have any left or x's on the left hand side of the equation. Right? These variables are separated, so y can be written explicitly as an expression in x's. And so everything we've done so far addresses this scenario. There's another scenario. So suppose I gave you this curve. Okay, so I draw this curve, and it's kind of messy. And while I'm cleaning it up, I can hear you in your mind saying, that's not the graph of a function. And you're right, it's not the graph of a function because it doesn't pass the vertical line test. Great, I'm glad that's where your gut went. But what I'll point out to you is that, no pun intended, is that if you pick any point on this circle, there's an area around the circle that is the graph of a function. Okay, so let me just make sure. This I intended to graph the set of points that satisfies x squared plus y squared equals 1, right? The unit circle. It's the set of points satisfying this equation there's not a graph, or there's not a function that gives us this as a graph. And what I'm saying is that pick a point on the circle, you can find a region of the circle that does pass the vertical line test. So it means that there is a function. That green part is the graph of some function f of x. Okay. So a function, let me write it this way. The existence of a function is implied, right? And that's where we're getting this idea of implicit differentiation. I don't know what the function is, but I do know that a region around this point does pass the vertical line test. So this arc here is the graph of some function. It's out there. I don't know what it is, but it's out there. And it turns out I can find its derivative. Even without knowing what the function is, I can find the derivative of that green arc. Okay, and that's what we'll talk about next. So let's take a 5-minute break. And I've got my coffee here, so I'm going to go and look and see if I can do something about these videos and the fact that they're private. So you can watch me get frustrated by YouTube if you would like. But I'm going to mute myself for 5 minutes, and I will see you back here at 8:55. All right, so it's 8:55. We had a 5-minute break. What I'm trying to do on YouTube is change videos so they're public. And YouTube tells me it's making those conversions. I'm not seeing that happen right now. So I will be patient and I will believe what I'm told by YouTube. Let's get back to implicit differentiation. I'm going to share my tablet. All right. So let's talk about implicit differentiation. So what's going to happen is that you're going to learn how to do the following. You're going to get an expression that involves one or more variables. It could involve 2, 3, 4, 5, and you're going to be asked to calculate a derivative, and I'm going to show you how to do it without having to get a formula like this. So let's do this first with the unit circle. So let's calculate the derivative of y with respect to x using this formula. Right, and so this is how we do it using implicit differentiation. So first, you just do a couple things. So I'm going to write this as a checklist. First item on your checklist is recognize the independent variable. So in our case, well, the independent variable is going to be what you're differentiating with respect to. So here we're looking for the rate of change of y with respect to x. That is asking how does y change as I change x. That means x here is the independent variable. Okay, so recognize the independent variable. The second thing I want you to do is recognize the dependent variable as a function of the independent variable. Okay, so that is to say, in our case, I want you to think of y as really being y of x. Okay. So you can rewrite the expression if you want to, and maybe we'll do that for the first couple examples we do. You can rewrite the expression, so replace y with a y of x if you want to, but you don't have to. In this process of implicit differentiation, you're going to act as if y is a y of x. You don't have to change it, but let's change it for fun. Okay, so let's write x squared plus y of x squared equals 1. Okay, so the second thing we do is differentiate both sides. Of our equation, right? So we've got this equation that we've rewritten as this, and now we want to differentiate both sides. And so we write d dx of the left side equals d dx of the right-hand side, right? We're differentiating both sides. We're doing the same things to both sides. That's perfectly fair. It continues to give us an equality. So on the right-hand side, I get 0 because the derivative of a constant is always 0. And on the left-hand side, I'll use the sum rule. Let's write it that way. And then you can see here we use the power rule, and here you use the chain rule. So the derivative of x squared is 2x, and the derivative of y squared is 2y times y prime. Or, and I prefer to write it this way, 2y times dy dx. And now is when you get excited, because you say, hey, I want to calculate dy dx. And you have a dy dx here. And so last, we solve the equation for dy dx. So in our case, that means you put all the terms that don't have a dy dx in it on one side of the equation, all the terms that do have dy dx in them on the other side of the equation, and you get this. And then you factor out a dy dx and look at what's left and divide both sides by it. So in our case, we get dy dx equals minus 2x over 2y, and you can simplify that to minus x over y. So there we go. This here is a formula for the derivative of y with respect to x. So you'll notice that the derivative formula has both x's and y's in it, and that's perfectly fine. What it just tells you is that pick an ordered pair that's on the graph, or pick an ordered pair that satisfies this equation, then the tangent line to this curve at the point xy is going to have that formula. So here's how we use that. I could say find, oh, come on, the equation, or actually, to be technically correct, find an equation of the line tangent to the unit circle at 1 over root 2, comma 1 over root 2. All right, so let's do that. Find an equation of the line tangent to this. Well, we've already computed the formula for the slope of that tangent line. So the slope of the tangent line is going to be minus the x coordinate, which is 1 over root 2, divided by the y coordinate, which is the same. And so we get minus 1. So that's the slope of the tangent line. What's the equation, or what's an equation of the tangent line? Well, we can use the point slope form, right? So we know we go through the point 1 over root 2, comma 1 over root 2. So we plug that into our point slope formula. And we now know our slope is negative 1. So I can even do better. I can just put a minus sign there. And there we go. That's the equation of our tangent line. So how do we check? Well, we're going to use my favorite tool. We're going to use Wolfram. So I want to make a remark about using Wolfram Alpha for this. So this right here is called, or the set of points that satisfy this equation is called an implicitly defined curve. So the set of x comma y in R2, where x squared plus y squared is called an implicitly defined, or we'll call it an implicit curve. It's a curve in the plane. So you can't just plot it using the same structure that we've plotted curves on Wolfram Alpha in the past. It's going to be very similar. We're going to say plot x squared plus y squared equals 1. And let's say 4. And now instead of just specifying the x input, which we could do if we had an explicit formula for our curve, like an explicit function, which we don't. Because we're defining an implicit curve, we need to list both our x values and our y values. Okay. So this is what I want to tell you about doing this on Wolfram Alpha, and probably even on Desmos, is that you've got to specify where in R2 you want to look for points that satisfy this equation. So let's go put Wolfram Alpha to work. So sharing my browser. Here's Wolfram Alpha. Let's plot x squared plus y squared equals 1 on so the language I used is slightly different in what I wrote down on my tablet. This should work too. Wolfram is a natural language processor. You can always check here, and if this makes sense, that's good. Oh, that doesn't. Oh, look at that. That should be equal. That makes a big difference. So there we go. There's our unit circle. So now let's look at our tangent line. So I'm going to see if it'll plot the point at which we're tangent. Let's see if it's smart enough to do that. It's not quite smart enough. Okay. Screw it. We'll just put. There's the equation of the tangent line we came up with. So we're going to plot our unit circle and our tangent line on the same square. Hit return. There we go. That looks good to me. And there you go. Does that look like a tangent line? Yeah. Thanks, Jesse. Thanks, Robert, for the thumbs up. Yeah, it definitely does look like a tangent line. So I have confidence that what we did was right. And this will work for almost any point on the unit circle. Can anybody speculate where this might fail to work? I'm going to bring us back to the iPad so you can see that formula. So looking at our work, can anybody speculate where this won't work? Finding a tangent line won't work?
When either x or y is 0?
Who was that? Was that Jesse?
Yeah.
Yeah. Okay, that's close. Very close. Very good. Anybody else want to take that and run with it?
Yeah, it should just be when y is 0 because it's a denominator.
Yeah. So when x is 0, so I drew a unit circle here at the bottom right. When x is 0, I've got the point 0, comma 1 on my circle, and I've got the point 0, comma -1 on my circle. And they both have perfectly good tangent lines that are horizontal. So you can see when x is 0 and y is 1 or -1, this quotient is 0. And that gives me a line that has slope 0, right? Which the picture here attests to. It's where y is 0, right here and right here, that this equation fails, right? The slope here fails because we can't allow for division by 0. When y is 0, then x is plus or minus 1, as you can see on the picture. I'm touching those points over on the bottom right. So you have plus or minus 1 over 0. That is undefined. So look at this picture down here. Can you see the geometry of that slope being undefined? What's happening at these 2 points where that formula doesn't work? Anybody see it? Ali, do you see what's happening here geometrically? That makes you say, oh yeah, that's why this formula doesn't work. No? Andre, how about you? What are the tangent lines doing at that point that make you say, oh yeah, of course that doesn't work? Athalia, how about you? What are the tangent lines doing at that point? Or what is the tangent line doing there? So Andre, you put in the chat, HOZ test, horizontal test. Yeah, Alexia, that's exactly right. The verticality. If you look at the tangent line here, it looks like it's going to be vertical. What's the slope of a vertical line?
Undefined.
Yeah, it's undefined. Okay, so the slope or this tangent line has an undefined slope. Hey, isn't that kind of convenient? So there's a consistency. This isn't a failure. The fact that this doesn't work at these 2 points isn't a failure. It's a consistency with the geometry. So that's kind of cool. I think it's kind of cool. Now, what if you wanted an equation of this tangent line? Well, you'd have to shift around and maybe rotate all of this by 90 degrees and think of the x coordinate as the dependent variable and the y coordinate as the independent variable. And then this arc could be the graph of a function that went this way. But we won't talk about that. Here's another cool. Let's do another curve. There's this curve. The book talks about it. So it's called the folium of Descartes. And it's defined by the equation x cubed plus y cubed equals k times x times y, where k is a constant that's bigger than or equal to 0. And just for the sake of what we're working on today, let's pick a number. Let's put 3. No, 6. So let's take a look at what the folium of Descartes looks like. And what we're going to do is we're going to want to calculate a formula for the slopes of the tangent line. So we're going to implicitly differentiate this in a second. But let's go and look at this sucker in Wolfram. So I'm back at Wolfram here. I'm going to scroll up, get rid of my tangent line. I'm going to put this folium of Descartes in. Y cubed or x cubed plus y cubed equals 6 times x times y. And this isn't something that you'll have to memorize. So there we go. I did it right on this. Oh, so I see these two curving cross lines. And I know the folium of Descartes is different from this. I'm missing some structure up here. So my window isn't big enough. So I need to make my window bigger. I'm going to make it go from 5 or -5 to 5 in both directions. Okay, yep, that looks good. That checks out. That's what I wanted to do. And there we go. Here's the folium of Descartes. Clearly not the graph of a function because it doesn't pass the vertical line test. But what I want to point out to you is it defines functions implicitly. There are implicit functions in this folium. I ask that you never look for them. They will just cause you heartache and grief. But here, let me just draw a sketch of the folium of Descartes. So it kind of goes like this. Okay. So let's look at pieces of this folium of Descartes that will pass the vertical line test. So over here, this all passes the vertical line test. And then I can keep going and it'll pass the vertical line test here until the graph kind of folds over here. And then if I keep, so let's see, if I go straight down to here, I can keep coloring red. And so my red curve there will pass the vertical line test. So all of that is a graph of a function. It's not a continuous function. And there's a corner, so it's not a differentiable function, but we're not worried about that. All that red curve is the graph of a single function, an explicit graph of a single function. I'm missing these other two black arcs. So here, this piece, the blue piece, that would pass a vertical line test. So that's the graph of a function. And this piece is a graph of a different function. So in the folium of Descartes, there are like 3 different explicit functions you'd need to graph that as a graph of functions. But we're not going to do that. We don't care. We're fine with the idea of an implicit function. We're fine with the idea of imagining that x is our independent variable. Well, so here, we want to find a formula for dy dx, the derivative of y with respect to x. So first thing we have to check is what's our independent variable, x. Our dependent variable is y. So we're fine thinking that y is implicitly a function of x. We're okay thinking this. Okay, so we're okay thinking that the equation we're given is actually an equation that looks like this. And I don't care what the formula for y is. So we'll take this and we'll differentiate both sides. So differentiate both sides with respect to x. You still get an equality because you're doing the same thing to both sides. On the left-hand side, we're going to use the sum rule. And the same thing on the right-hand side. Well, on the right-hand side, we're using the product rule, actually, right? Because we've got 2 functions. We've got the 6x times y of x. So we've got the derivative of 6x times y of x plus 6x times the derivative of y of x. I'm just going to write that as dy dx. So let me economize with my space. So the derivative of x cubed is 3x squared. The derivative of y cubed by the chain rule is 3y squared times dy dx. And then the other side, I got the derivative of 6x, which is 6 times y of x, then plus 6x dy dx. So that's what I get taking the derivative of both sides. Now, the next step is look for all the terms that have my derivative in them, and I want to get those all on the same side of my equality. So I have 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. And on the side with the dy dx's, I'm going to want to factor them out. I'm going to pull them out. You have to factor them out from the left-hand side. So let's see how this works. Bring this to the next page. So I get dy dx, 3y squared minus 6x equals 6y minus 3x squared. And now, since I'm interested in dy dx, I'm going to divide both sides by this. Dy dx equals 6y minus 3x squared over 3y squared minus 6x. And the top and the bottom, I can factor out a 3, and I get 2y minus x squared over y squared minus 2. 2y minus x squared over y squared minus 2x. And there we go. There's the formula for my derivative. You'll notice there was some point, like from here to here, where I stopped writing y as a function of x and just started writing y down, because this notation no longer serves us. And I think this is the last time I'm probably going to switch from a y to a y of x, because we can all imagine that. We don't have to write that down. All right, so that's implicit differentiation, calculating a derivative of our output without an explicit formula. The trade-off is that the formula for our derivative is going to involve both our independent variable and our dependent variable. And that's fine, because you'll be given an ordered pair to plug in, or you'll be able to figure out what it is. So let's do an example with this folium of Descartes. So let's verify that a point is on a folium of Descartes. Oh no. Let's not start that way. Let's find where the tangent lines to the folium of Descartes are horizontal. Okay. So that means that if we've got the folium of Descartes, I think this is the right formula. In using the language of calculus, we want to know where is the derivative of y with respect to x equal to 0. So that's the question we want to answer. Where are the tangent lines horizontal? That's the same thing as saying where's the derivative equal to 0. Okay, so, well, we just calculated the formula for the derivative. So we need to solve 0 equals 2y minus x squared over y squared minus 2x. So to solve that, we can multiply both sides by the denominator on the right. So those cancel. And on the left-hand side, we get 0. So I get 0 equals 2y minus x squared. All right? Adding x squared to both sides, I get that. All right. Well, what does that tell me? That tells me every time the y value is twice the square of the x value, my tangent line is horizontal. This is the equation of a parabola. But my folium of Descartes looks like this. And so it looks like it's saying wherever I'm on this, oh, so there's a point right there. Oh, and I can see that, right? Here's a point where the tangent line is horizontal. Can you see anywhere else that the tangent line is horizontal? I don't see any down here. So here's the point we just saw. Oh, right about here, the tangent line looks horizontal, and then it's not horizontal anymore. So it looks to me like there's 2 points here where the tangent line is horizontal. And that equation that we just showed seems to suggest that they're on this parabola. But I'm not sure exactly what's that's telling us. Oh, these give us the ordered pairs that are on the folium. And if our ordered pair satisfies this and this, then our derivative is 0. That's it. Okay. So here I know how my x and y coordinates are related. I need to use that and this to figure out the actual ordered pairs. Okay. So let's do that. So I'm going to take this, and wherever there's a y, wherever there's, I'm going to sub that into here. So I think wherever there's a y, I'm going to put half x squared. Let's see how that works. So x squared equals 2y, and x cubed plus y cubed equals 6xy. So substituting in, I get x cubed plus 1/2 x squared to the 3rd power equals 6x times 1/2 x squared. Right. Again, wherever there's a y, I'm substituting in 1/2 x squared because I'm solving that for y. There's a y here to the 3rd power. There's my y to the 3rd power. So what do I get? I get x cubed plus 1/8 x to the 6th equals 6x times 1/2 times x cubed. And this is 3 times x to the 4th. Did I do that right? No. And that's supposed to be a 2. So that's supposed to be a 3. So I've got an x cubed here. I've got 3x cubes there. So I can rewrite this, subtracting an x cubed from both sides as this. And I can multiply both sides by 8 just to clean it up a little bit, and I get that. All right, so that's interesting. And I want to know for what x's solve this equation. And again, these are the points on the folium. Right? They're the points in here where the derivative is 0. So, and here. So on the folium where the derivative is 0. If we go back and look at the picture, we think we see a horizontal tangent line here and here. So I think there's going to be 2 solutions from the geometry. So I expect that there's 2 solutions here. But Dr. Miller, you say this looks like it's a degree 6 polynomial. Right? So there could be up to 6 from the fundamental theorem of algebra. Yeah, that's right. But let's see what happens. So I'm going to get everything onto the left-hand side. So I get a polynomial equal to 0. So I'm looking for the zeros for this thing. Over on this side, I see I've got an x cubed in both terms. I can factor that out. X cubed times x cubed minus 16 equals 0. So this means that either x cubed equals 0 or x cubed minus 16 equals 0. So these are the solutions that we're looking for. So x cubed equals 0, that happens only when x equals 0. Take the cube root of both sides here if you like. And this is good. This makes me happy because going back to the graph, that gives me the origin. Right? That's where we thought one horizontal line is. So sweet. Now it looks like we're just looking for that location. So hopefully this will give up that number. So what I want you to recall, and if you don't remember this, that's fine. This is just kind of a fancy way of me saying, hey, there's some algebra that you may need to remember here. There's this idea that if you have the difference of two cubes, you can always write that in this way. You can factor it in this way as x minus a times x squared. So where did I write this formula down? X squared plus ax plus a squared. And then if you use the quadratic formula on this quadratic term, it will tell you that this is irreducible. That means it can't be factored. And that's good because that tells us that this difference of 2 cubed only has 1 0, which is kind of what we were hoping for. So in our case, here's 1 cubed, and I'm going to write this as a cube, right? 16 is the cube of the cube root of 16. So that tells me x cubed minus 16 equals x minus the cube root of 16 times x squared plus the cube root of 16 times x plus 16 to the 2/3, right? That's the cube root of 16 squared. So this is telling me where the other 0 is. So use a calculator, and I think you'll see that the cube root of 16 is approximately equal to where did I write that down? 2.519842. So this is our other calculation. So x equals 0 and x equals the cube root of 16. So let's hopefully, if we go back and look at the graph, hopefully we'll see that this point is at the correct location. So let's do it. Let's look back at, Wolfram Alpha. So I'm going to share my browser again. Here's the full name of the cart that we plotted. Let's look at the x-axis and go to 2.5. So here's 2, here's 4. So this must be 3. So this must be 2.5. The web browser isn't giving me a way to track where my mouse is, so I'll do the best I can. So I'm going to go straight up from about 2.5. Looking good. Looking good. I think that cube root of 16 is the x coordinate of where my tangent line is horizontal. So I believe our work. There's a matter of finding what the y coordinate is, but I can just plug it, cube root of 16, into my full name of Descartes and compute with that. So long problem, finding where a tangent line is horizontal, but the only new element of this problem was the idea of implicit differentiation. Okay. So you have all the tools to do problems like this. Let's do another problem. So consider this equation. It defines, I need to share my tablet again. X squared minus y squared equals 4. It defines a curve in the plane implicitly. Here I'm not writing y as a function of x, so x is a function of y. So take a minute and use implicit differentiation to find dy dx. So pull out a piece of scratch paper, or write in the margin of your notes, or directly in your notes, computations for finding the derivative dy dx. I'm going to give you 2 minutes. And if you come up with something, privately send a chat to somebody else in the class. All right, how'd that go? Anybody get a formula for the derivative? Robert still working? All right, so who got something in Zoom, indicating in Zoom somehow, who got something for the derivative? Robert got something? Doesn't have to be right. Who didn't get anything? Who got stuck? Okay. So what was step one? Can somebody tell me when I went, started talking about this stuff, I kind of gave you some steps. Can somebody tell me what the first step in calculating an implicit derivative is? Identify the, no, Andre, that's like step 3. The first step is to identify the blank.
Independent variable.
Independent variable, right. So in this case, what's our independent variable?
X squared.
Nope. You're making it more complicated. It's just a variable, right? It's not an expression, it's a variable.
Oh, X.
X, yeah. How do I know my independent variable is X?
We just know. We have
No, it's actually more explicit than that. Jesse, you unmuted. Do you want to say something?
Yeah, you're being asked to derive y in relation to x.
Okay. Yeah, well, I'm asking you to do that. What is that? How does that answer the question?
That means that y is the dependent variable and x is the independent variable.
Exactly. If you're asked to find this, and I just circled it, that means upstairs, that gives you the dependent variable. So this, in this case, y is the dependent variable. But to answer the question I asked, what's the independent variable? That's down here in the bottom. Good, Alexia?
yeah.
Okay, so great. So what's the independent variable? It's X. What's the dependent variable? It's Y. So what you want to think of quietly into yourself is you want to think of Y is your implicit function. Think of Y really as a function of X. Okay, so once you're in that mindset, what do you do next, Jet? What do you do next, Jet? No? Anybody? What's the next step?
You plug it into the equation up there, x squared minus y x squared.
You could, right? You could rewrite your equation with that explicit function notation. And as you're learning this, maybe that's a good idea. So I'll give you that, Robert. But once you have the formula down and you're ready to look for the derivative, what do you have to do?
You have to take the derivative of both sides.
Yeah, that's the next step. Once you're in the mindset that y is a function of x, then you're ready to differentiate both sides. And when you're here, now just let your instincts and your experience take over. On the right-hand side, the derivative of a constant is 0. On the left-hand side, the derivative of a difference is the difference of the derivatives, right? Use these differentiation rules. And then the derivative of x squared, the derivative with respect to x of x squared, power rule, 2x. And then it's when you come to differentiate anything with your dependent variable in it that you remind yourself, oh, I'm in this mindset. So this really is a composition of functions. And so I need to use the chain rule. Okay. So let me, at the risk of making things complicated, when I was learning this for the first time, this is how I reminded myself how implicit differentiation works. Okay. I reminded myself, y is the dependent variable. And then I told myself, well, treat it like it's a regular variable. Okay. So just like here, the derivative of y squared, use the power rule, you get 2i. Okay. And then when you differentiate it, just tack on a dy dx at the end. That is to say, when you differentiate x squared minus y squared, you're going to get a 2x and a 2y. But because this is the dependent variable, you tack on a dy dx. And that's a way you don't overthink what's going on. Okay. So procedurally, algorithmically, symbolically, that's all that's happening. Whenever you differentiate something that involves a y, you tack on a dy dx. Okay. All right. I want to back to the work. I want to find dy dx. What's the next thing I do? Somebody who hasn't said anything yet, like Selena or Brandon or Summer or Haven. What's the next thing I do? Anybody want to guess?
So you isolate the independent variable, or you by subtracting the 2x to the right side, and then leave everything else on the left.
Right. So I'm going to take this 2x and I'm going to move it over to the other side of the equation because I want to isolate this symbol. Right, Jet, you said independent variable, but you meant to say this symbol. I want to isolate this symbol.
Yeah.
Yeah. So
That thing.
yeah, that thing. So I think minus 2y dy dx equals minus 2x. And now you're looking for this. Just we talked about this last time. When you're working on a problem, you need to know where you're starting and where you want to end. And then you build a road of logical deductions from the beginning to the end. And the end is finding dy dx. So if you got an expression like this, or heck, if you got an expression like this here, you want to get dy dx by itself. So you solve for dy dx. This is the first step in doing it. Then you divide both sides by negative 2y. And then simplify. And you get x minus y. So dy dx is, x over y. And that's your answer. Okay, should we do another one?
Wait, can you hold it there for a second?
I would be happy to.
Yeah, because it was lagging. and
Okay.
just saw what it said. Thank you.
Does anybody want me to go back? Because I flipped back and forth a little bit. Is everybody good? So let's review this again, and then I'm going to give you a new equation and ask you to do the same thing. Find dy dx. So you have an equation that has x's and y's in it. I ask you to find dy dx. You identify the independent variable. Blah, blah, blah. You identify the dependent variable. Beep, beep, beep. Okay, in your mind, you're just identifying that in your mind. Okay. Then you differentiate both sides. Use the normal rules for differentiation. But then whenever you differentiate the dependent variable, slap on a dy dx at the end. You'll get a formula that will involve x's, y's, and dy dx's. And then solve that formula for dy dx. You should always be able to do that in this process. Okay, you ready to try that yourself? Well, ready or not, you're going to do it. All right, find dy dx if x cubed y plus y squared equals xy. All right, so 3, 2, 1, a 3, 2, 1 go question. What's the independent variable? 3, 2, 1, go. Yeah, it's x. And 3, 2, 1, go. What is the dependent variable? 3, 2, 1, go. And I've been very nice to you, right? I've been consistent with the symbols I've been using for each of these. So you could have guessed it and got it right. But make sure that you're going through the process. Now, what's the next thing I want to do? So this will be the last 3, 2, 1, go question before I ask you to start computing. Oh man, we're just out of time. Gee, crickets. All right, got to stop here. So what I want you to do is calculate this. And the answer should be I got 1/2 times 1 minus 3x squared. There was a bunch of simplification. So test yourself today. Okay. But we're out of time. I don't want to take more of your time. Yeah, I've got office hours at noon. If you've got questions, I will slowly, it looks like I have to manually convert all my videos by hand to public. I'll do that as soon as I can. So hang in there, stay healthy, stay safe, and I will see you Monday. Oh yeah, Lupe's drop-in hour at the STEM Center today, 7:30. Thanks for doing that, Lupe.
I also had a really quick question.
Yeah, Robert.
Are you gonna start grading quizzes again? Because I've done 4 so far and they haven't been graded yet.
Oh, you haven't gotten scores back?
No.
Okay. All right. Let me go take a look at that.
All right, and I think I might have failed like 2 of those.
Oh, that's all right.
So I'm trying to like brush up on whatever I messed up on.
Yeah. Okay. I'll go double check that after class, after
right.
my other class. So during office hours. Thanks for letting me know, Robert.
Thank you.
Yep. Bye-bye.
Oh yeah, Professor, the same thing for mine too. I've done like 4 or 5 quizzes.
Oh man. Okay. Yeah. Definitely. I'll check that out during office hours today.
And I
After I
had,
teach.
sorry, I had emailed you because I failed one of them. And then I submitted the failed one and I like wrote you an email telling you I failed it. And then I went and saw Lupe and we went over it and then I retook it.
Okay.
So you'll see it's like L2. So,
Okay. I'll double check that out. Thanks for letting me know, Alexia.
of course. Thank you.
You bet. All right, Lupe, Thursday, 3?
Yes.
Okay. I'll see you there then.
Okay. Bye.
Bye.